Ever wondered about the exact speed of a car? Not over an hour or even a minute, but at one single instant? That question right there is the key to unlocking one of the biggest ideas in all of math, the derivative. Now, I know it sounds super complicated, but today we're going to cut through all the noise and show you how simple and powerful this cornerstone of calculus really is. So here's the game plan. First, we'll nail down the main concept, the big idea behind it all. Then I'm going to give you your first most important tool, the power rule. After that, we'll see how to combine our tools to solve bigger problems. And finally, we'll put it all together to find the exact slope at any point on a curve. Let's do this.
All right, let's dive right into the heart of it all, the big idea.
Okay, so forget all the scary formulas for just a second. When you hear that word derivative, what's the one thing you should actually be thinking about? Well, it boils down to something that's honestly pretty simple.
Yep, that's it. A derivative is basically a slope-finding machine. Seriously, you give it a function and it builds you a new function. And the only job of that new function is to tell you how steep the original curve is at any single point you want to look at. Let's make this super clear. Imagine the graph of y equals 8. What does that look like? It's just a perfectly flat horizontal line, right? So what's the slope of a flat line? It's 0. It's not going up, it's not going down. So the derivative of a constant like 8 is just 0. Our slope-finding machine is telling us, hey, the slope is 0 everywhere on this line. Makes sense. And this brings us to a really, really important idea. Back in algebra, you probably found the slope using 2 points on a line. That gives you the average slope between those points. But a derivative is way more powerful. It gives you the slope of the tangent line. That's a line that just barely kisses the curve at one single point. It's the slope at that one specific instantaneous moment. Okay, so we know a derivative finds the slope at one point. But how do we actually calculate it? We're not just going to guess, right? Of course not. It is time to get our hands on the first and honestly, the most important tool you're going to need. Now, the really formal, by-the-book way of finding a derivative involves something called limits. And trust me, it can be a total headache. But lucky for us, calculus gives us this incredible shortcut that works on a ton of the functions you'll ever see. This shortcut is called the power rule, and it is an absolute game changer. I know, this looks a little scary, but I promise you, it's just a simple two-step recipe. All it's saying is this: to find the derivative of x to some power, you just do two things. 1, you bring the original power down in front, and 2, you subtract 1 from that original power. That's it. That's the whole move. Let's walk through it with x squared. Our exponent here is 2. So step 1, we bring that 2 down in front of the x. Step 2, we subtract 1 from the original exponent. So 2 minus 1 is just 1. What's left? 2 times x to the power of 1, which is just 2x. The derivative of x squared is 2x. Simple as that. And that is why the power rule is so amazing. It's like your secret code, your master key that lets you skip all the complicated theory and just get right to the answer for so many different functions. So we've got the power rule down, but what happens when the problems get a little more, complicated? Well, let's expand our toolkit and see how we can use this rule with another simple idea to tackle bigger stuff. So, what do you do if there is a number multiplied out front, like 7x squared? It's actually super easy. The constant multiple rule just says that number, the constant, it just comes along for the ride. You kind of ignore it for a second, find the derivative of the x part, and then just multiply it back in at the end. Let's try it with 7x squared. First, we just park that 7 off to the side. Then we take the derivative of x squared, which we already know is 2x. And for the final step, we just multiply that 7 back in. So 7 times 2x is 14x, and we're done. And this, right here, is where it all clicks. When you see a big, long function like this, you don't have to panic. You just treat it like an assembly line, one piece at a time. The derivative of x cubed, power rule says that's 3x squared. The next piece, 7x squared, we just did that one, it's 14x. And the last piece, negative 8x, that's just negative 8. You solve each little part and then just string them all back together for the final answer. Okay, so we've been busy making these new functions we're calling derivatives, but we can't forget our original mission. What's the whole point of doing all this? Well, in this last part, we're going to use our new toolkit to finally answer that question and find a real concrete slope. All right, here's the challenge. We've got the function x cubed,
it makes a nice curvy line. What I want to know is, what is the exact steepness of that curve at the single instant where x is equal to 2? Not an average, but the slope right at that one tiny point.
And it's a really simple two-step solution. First, we need our slope-finding machine. So we find the derivative of x cubed. Using our good friend the power rule, that gives us 3x squared. Now that we have our tool, we can move to step 2. We just plug in our x value, which is 2, into that derivative. So we get 3 times 2 squared. And that gets us our answer. 2 squared is 4, times 3 is 12. The slope is exactly 12. And that's the whole point. That number, 12, isn't just random. It is the precise slope of the function x cubed at the exact moment where x equals 2. We took a general idea, built a tool to analyze it, and got a concrete number describing its rate of change at one instant. That, my friends, is the power of the derivative. And this isn't just about curvy lines on a graph. Derivatives are used everywhere to find the instantaneous speed of a rocket, the rate of growth of a company, or how fast a disease is spreading. You now have a tool that can measure the rate of change at any single moment. So the real question is, what are you going to measure?